Hey everybody, Mr. Covey here. First things first, wipe away your tears. I know you're sad that I'm not there, but it'll be okay. I'll be back on Monday. Okay, first thing I'd like you to do is take the derivative of these three equations with respect to time. So with respect to t. Pause the video, do that, and then come back and check your answers. Okay, so there are your answers. This relates back to what we were talking about last class period. There are no t's here. There is no time represented. So if we're differentiating with respect to time, every time we take a derivative, we need to say, oh, we took the derivative of an x term, but really we want to take the derivative with respect to t. So we need to add that for every term. Over here, the derivative of a is just 1, but we took the derivative of a not with respect to t, so we need to add dA dt. And again here, derivative with respect to r, add dr dt. Okay? And the last one is similar. Make sure you understand that concept before you move on. Okay, so now we're going to look at a application problem. These are called related rates problems. You'll see why in a second. So this problem says a circle is growing with time and the radius is increasing at a rate of 3 meters per second. Find the rate at which the area is growing when the circle has a radius of 10 meters. Okay. First thing we're going to do is draw a picture. We are talking about a circle. They tell us the radius is growing at a rate of 3 meters per second, and they want us to find the rate at which the area is growing when the radius is 10 meters. So what we're trying to find is the rate of change of the area. Another way to say that is we're trying to find the slope of the area with respect to time. We are trying to find the derivative of area with respect to time. This is what we are trying to find. The rate of change of area as time changes. It's the slope of area with respect to time. So this is what we're trying to find. Next, we need to write down what information we are given. So we are given that the radius is 10 meters, and we are given that the rate of change of the radius is 3 meters per second. The rate of change, the slope of the radius with respect to time, is 3 meters per second. So we know the rate of change of the radius, and we know the radius, and we want to find the rate of change of the area at a certain moment. The next thing we need to do is somehow relate the radius of a circle to the area of a circle. Well, hopefully you remember from your geometry days that the area of a circle is pi r squared. Once you have that relationship, now we differentiate with respect to time. This is what you did in your warm-up. So the derivative of a is just 1. But we took the derivative of an a term, not time, so we need to add dA dt. The derivative of pi r squared is just bring down the 2 pi r, add a dr dt. Okay? At this point, we're allowed to start subbing things in, not before this point. So dA dt is what we are trying to find, so we don't know what that is. We know our radius at this moment in time is 10, so we sub in 10 for r. And we know that dr dt is 3. Calculating this out, the rate of change of the area is 60 pi. And since it's area, it's meters squared per second. And that's our final answer. to give you a quick visual of what this problem is really saying, we have a circle that's growing. The radius is growing at a constant rate. That does not mean the area is going to grow at a constant rate. Depending on the size of the circle, the area is going to be growing at a different rate. So here's a little animation to see that. Although your radius is going up at a constant rate, your area is actually going steeper and steeper and steeper depending on the radius. So what we are doing is we are picking a point in time, and we're really finding the slope of the area. We're finding the rate of change of the area. Even though the radius is increasing at a constant rate, the slope of the area changes, and we're finding the slope of the area at a single point. We will talk more about what this exactly means in class on Monday. Let's look at another example problem. I'm also going to lay out the steps very explicitly when we do this example. Okay, so it's March 22nd, so you decide to throw Mr. Covey a birthday party. Smart idea. You decide you want to blow up balloons. They are spherical balloons. As you're blowing it up, you notice that the volume is changing at a rate of 13 inches cubed per second. And you wonder how much the radius is changing when the radius is 5 inches. Our first step is going to be to draw a picture. Okay, so we draw a picture. We're talking about a balloon being blown up, and we're talking at the moment when it has a radius of 5 inches. Sliding up to our steps here. First step, draw a picture. Okay, going back down here, our second step is going to be to state what we are trying to find. So what we're trying to find is how much the radius is changing. We're trying to find the rate of change of the radius. In other words, the slope of the radius with respect to time. So we're trying to find dr dt. This is what we are trying to find. Sliding up to our notes here, second step, state what you're trying to find. I want to be clear, we're not trying to find the radius, we're trying to find the rate of change of the radius. We're not trying to find r, we're trying to find dr dt. Next step is to state what information we're given. So we are given that the volume is changing at a rate of 13 inches cubed per second. So the rate of change, the slope of the volume, is 13. And we're also considering just a single point in time. We're considering the exact time when the radius is 5 inches. So third step is to state the given information. Okay. Next, we need to set up some equation that relates the quantities we're talking about. So how does the radius of a sphere relate to the volume? Well, if you remember from your geometry days, the volume of a sphere equals 4/3 pi r cubed. So our next step here is to write an equation that relates the quantities, the variables involved. This is usually geometric. In the last one, it was an area of a circle. Here, it's the volume of a sphere. It might be Pythagorean theorem. It might be something else that you learned in geometry. Okay? So once you set up that equation, again, we have not subbed anything in yet. What we need to do now is differentiate with respect to time. So the derivative of d is just 1, but we need to add a dv dt because we are differentiating with respect to time. The derivative of this will bring down the 3, so it'll just be 4 pi r squared, but we need to add a dr dt. Okay, so going back up to our steps, our next step is to differentiate with respect to time. Now we're here, and now we can sub in anything we know. So we know dv dt is 13. We said that up here. And we know r is 5. So sub in 5 for r. So our sixth step is to sub in any given information. And our last step here is just to solve for whatever we're trying to find. So we want to figure out dr dt. So let's calculate this out. We got 13 equals 5 squared, 25. 25 times 4 is 100. So equals 100 pi dr dt. And now we just divide both sides by 100 pi. And we're done. dr dt equals 13 divided by 100 pi. That's the rate of change of the radius is 13 divided by 100 pi. If you wanted to get a decimal, it's 0.041. And again, we're talking about the rate of change of the radius, and we're talking everything in inches. So it'd be 0.041 inches per second. That's the rate of change. That's the slope of the radius. Coming back up here, our sixth step is just to solve for whatever you're trying to find. I know there's a lot of steps here. You guys will get better at them. You're going to spend several days practicing. But stick with me for one more example here. So it says a 25-foot long ladder is leaning against the wall and sliding towards the floor. If the foot of the ladder is sliding away from the base of the wall at a rate of 15 feet per second, how fast is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground? Okay, let's start by drawing a picture. Okay, so we have a ladder leaning up against the wall. We know that the ladder is 25 feet long. That's how long the ladder is. The ladder's length isn't changing. It's sliding towards the floor. So the bottom part's sliding out, and the top part is sliding down. So that's our picture so far. It's asking us about a specific point in time, specifically when the top of the ladder is 7 feet from the ground. So when that distance is 7 feet. Okay? Let's come over here and figure out exactly what we are trying to find. So we're trying to find how fast the ladder is sliding down the wall. So how fast this side's coming down that wall. Let's throw some variables here. Let's call this side x. Let's call this side y. And what we are trying to find is the rate of change of this x side. In other words, we're trying to find the rate of change of x, how that side length x is changing as time changes. So this is what we are trying to find. What we are given is that x equals 7. We are given that the ladder is 25. And we're also given that the foot of the ladder is sliding away from the base of the wall at a rate of 15 feet per second. So this length is changing at a rate of 15 feet per second. In other words, the rate of change with respect to time of that length y is 15 feet per second. Okay? Looking back here, we need to set up some type of geometric relationship between the quantities we have in this picture. Hopefully you recognize that it's a right triangle. When you think right triangle, you think Pythagorean theorem. So we can set the following relationship. Note that we don't sub in 7 for x right away because that quantity is changing. So we can't sub that in right away. And we'll talk more about that. All right, now that we have our equation set up, let's differentiate with respect to time. We should get that. Now let's sub in the quantities that we know. And we have a problem. There's two things we don't know. dx dt, which is what we're trying to find, but we also don't know y. Looking back at our picture, we can actually figure out y at this point in time. We can use Pythagorean theorem. So let's do a little side project here where we find y in this triangle. Okay, so you should get y as 24. So coming back here, let's sub in 24 for y. And now we have an equation with only one thing that we don't know, dx dt, so we can solve for dx dt. And that should be your final answer. I want you to work on some of these practice problems. See if you can get this process down. On Monday, we will discuss what this all means a little bit more and look at some examples to try and help us understand this more. That is all.